In this video, we'll go over the absolute basics of ORCA calculations, so you can get started pretty quickly running actual calculations and learning this way. So I'm going to assume that you have already installed ORCA, so for example on Linux you should have the ORCA command here, which produces this output if you don't specify an input file. There's also another ORCA program, which is a text-to-speech program, which is not relevant here. So you might want to verify that the ORCA command actually calls ORCA. And now we just need to create an input file. So we'll start with a very simple example. So dihydrogen. So we'll create an input file like this. And then there's really two parts that you need for an input file in ORCA. So there's the command line, which starts with an exclamation mark like this, and it will specify all the calculation types and method you're going to use for the calculation. So for example, we'll do a single point energy calculation, so SP, and then we'll choose some DFT functional, M06 for example, and then we can specify a basis set, so def2 SVP for example, and that's really all you need. And you can change the parameters based on what method you want to use, and you can compare different methods, but the syntax is going to always remain the same. The next line is actually the structure, so you're going to have asterisks, XYZ, and then charge and multiplicity for the structure. So if it's a neutral molecule, we'll have 0. If it's a cation, you will have 1. An ion, you have -1, etc. And then the multiplicity, which in most molecules, which don't have radicals, would be just 1. So in our case, it's just 1 because all the electrons are paired. And then you end the XYZ block with other asterisks, and in between these you have the actual XYZ structure. So in this case, if we want dihydrogen, we'll specify the atom first, so hydrogen, and then the XYZ positions. So this is kind of arbitrary, but we'll put the first hydrogen at the origin, and then you can put the second hydrogen, let's say 1 angstrom away in one direction, and that's basically our input file. So you can just save exit out of it and run this input file, and we see we have a bunch of output, but the main important information we get from this output is of course the energy, the actual SCF energy. So this is the electronic energy plus the repulsion between the nuclei, and that's the main energy you want to use for further treatment. And now we'll get into some more advanced topics about the main calculations you're going to perform. So first, we'll perform a geometrical optimization. So we want to find the equilibrium structure with this method. So we've just specified a random XYZ structure, but we don't know what is the most stable XYZ structure for this molecule. And the geometrical optimization allows you to find this equilibrium structure, so the minimum in energy. So to perform the optimization, we can open back the file and just change the SP for opt for optimization, and then do the same thing, just run it. And it takes a bit longer, it goes through a couple cycles, and then you can see it finishes, and we have the energy here. And as well, if you look in the files, you have here calc.xyz, which is the equilibrium structure. So you can open it, and you can see the XYZ structure is different from what we put in at first. This is the optimized structure, so these coordinates have been optimized. So you see the hydrogens are much closer together than 1 angstrom, which was our initial guess. Another file you might want to look at is the calc underscore trj.xyz, which is the trajectory of the optimization basically. So it's all the steps taken in the optimization before reaching this final structure. So if something goes wrong, you can always look at these structure and just pick the last one and go on from there.